Hello, everybody. I'm Monica Beckwith. I'm a performance engineer. I'm going to talk about HotSpot, which is a Java virtual machine. I'm going to talk about the what makes up the virtual machine and how, from performance standpoint, how there are various optimizations in the virtual machine that we already are taking advantage of, or we can, depending on the version of Java that you're at. So a little bit about me. Like I said, I'm a performance engineer. I worked with with Java Virtual Machine for more than a decade, especially with HotSpot, which is like Sun Oracle's virtual machine. We also have worked on the OpenJDK hotspot, which is a similar, maybe this is on? I was getting a feedback. I was wondering. Okay, all right. So OpenJDK hotspot is also the same thing. So when changes are made to the hotspot virtual machine, most of them are propagated into the OpenJDK. So I worked with Sun Oracle, and before that I worked with Advanced Micro Devices. I was working on their new Optron 64-bit processor, and we were trying to do optimizations with respect to static compilers, dynamic compilers. So that's how I got into Java virtual machines. At Oracle and Sun, I worked not only with the JVM, but also with JIT heuristics and JIT compilation, garbage collections also. So my last title at Oracle was Garbage First, Garbage Collector, Performance Lead. And now I'm a consultant. I've been working as a consultant for about 3 to 4 years now. I optimize, manage runtime applications. One of the reasons I wanted to give this talk is because it's really important as a performance engineer to understand what you're trying to tune. So, and one of the reasons I went into performance engineering is because I really like the VM, the garbage collection, and I could see various ways to improve certain things. And with this knowledge, hopefully you will go back. If you're working with the virtual machine, you can go back and take these optimizations to your place of work and try them out if you haven't tried them out already. So this is the agenda. Since I'm going to talk about the virtual machine, I'm going to talk about its components. So there's the execution engine and the runtime. So I'm going to talk about those. Those I call them the helpers because that's what kind of helps the virtual machine function. The other part of it is performance engineering. So I'm going to talk about the trifecta of performance engineering. What drives these innovations into the virtual machine? So basically the footprint, the throughput, and latency, which is also known as responsiveness. And then finally, we'll dive into these and try to see how these, like how the footprint, throughput, and latency, how that influences the virtual machine itself. So let's look at the virtual machine. In a simplified form, we have your Java application, and then it runs on top of the virtual machine, which I call the Java VM. And then you have the operating system and hardware. It could be like, you could be running it on the cloud or whatever. So basically, the gist is that your virtual machine and your Java API forms your JRE. JRE is your Java runtime environment. That's what most of you guys download on your phones or on your cloud system applications or whatever. So whenever you're downloading something, that's a JRE mostly. Many people who work with the development kit, they download the JDK. So JDK is also this plus tools, basically, some built-in tools like JConsole and stuff like that. Okay. So let's talk about the helpers. Like I said, helpers are the runtime and the execution engine. So the execution engine itself, there are two components. First is the heap management, which is known as garbage collection. And then the second is compilation. So we all know about the JIT compiler. So that's what I'm talking about when I'm talking about the compilation. So let's talk briefly about the heap management aspect of it. So we know heap management, garbage collection, we all know is reclamation, right? You're reclaiming back your heap. But there's also an aspect of to heap management, which is allocation, taking control of your allocation. And how that is important, I'll talk about it when I'm talking about the performance trifecta. Okay? And like I said, when you're talking about optimization, you're talking about compilation, we straight away think about static compilation. Most of simpler optimizations in the dynamic compiler come from the static compilation world too. So one of those is like ahead-of-time compilation. So instead of doing just-in-time compilation, if we know there's a particular library that's going to be used often or some shared code, then we can compile it ahead of time and then use it when we're compiling our application. So we already have pre-compiled code. So that's what ahead-of-time compilation gives us. For HotSpot JVM, Java 9 is the first release that will have ahead-of-time compilation. And I think it's just the base of the modular Java 9, and there's a base, and that particular aspect is ahead-of-time compiled, because base is used in every application. So there are two main aspects, I would say. One is the profile-guided optimization, and then the other one is adaptive optimization. So for HotSpot virtual machine, these are the two backbones. So from the get-go, like maybe from Java 1 point whatever, we did a little bit of, we had different compilation levels like server and client. And then there was, to be able to go from one to the other, there were thresholds. And as your application would run, like go from warm-up to steady state, you would cross these thresholds for your hot code. So whatever your application whatever is hot for your application, that's what the JVM finds out because of the number of invocations that you have. And that's one of the ways that it does profile-guided optimization. It has been improved further by tiered compilation and stuff like that. And if I get a chance, we'll talk more about that. And similarly, we have adaptive optimization, such as inlining, such as deoptimizations, and I'll talk about that as well. But those two make up the HotSpot virtual machine. And then AOT just got added in its simplified form in Java 9. So what about runtime? So we all know the most so that's how your code is interpreted first at the very beginning. As soon as you start running, at startup, that's what you get. You get simple interpreted code. Eventually, it'll go based on, like I said, thresholds and stuff like that. It'll go into different tier levels and get compiled at different efficiencies. What else does the runtime do? It does class loading and various other things. Thread management, synchronization. I'm not going to cover more of these, but when I'm talking about optimizations, I may talk about synchronization and stuff like that. But if you want to read, of course, please go ahead and look at the OpenJDK Java.net page, and it gives you a good overview of the runtime of the HotSpot VM. So when we talk about runtime, there's only one goal. Runtime only has one goal, and that's converting bytecode to native code, right? And so that's why interpreter is how it starts. And then the compilation happens, and then you have optimized code spewed as a part of the JIT compilation, adaptive optimization. But the goal is bytecode to native code. That's simple as that. So you have your Java bytecode converted to native code. You execute the native code on your hardware. So now we understand the execution engine. We understand the runtime. So what does that have to do with performance? So what drives innovations in performance? There's the three aspects of it. The responsiveness is the first one, footprint is the next one, and throughput. So if I send a stimulus, how soon am I going to get it back? That's what responsiveness is. So you have your system, you send in a stimulus, maybe to a block of it or to the entire system, right? So how soon do you get it back? And that's a responsiveness, either of the entire system or components of that system. Footprint is very simply, it's how much memory you're consuming. You know, not just your heap, but your process itself. How much memory is it consuming? And can I fit in more? Can I compact it? You know, those are the optimizations that drive innovations in the JVM itself, okay? Throughput. How can I maximize the usage of my system? Operations per second. I want to have the most pushed in through my system. I want the JVM to do its best to optimize the code, generated code to its optimal sequence and execute it. I don't want the garbage collection to be a pain, you know, and I'll talk more about that. But the goal is that my application should be doing its work most of the time. That's the goal, so that's the throughput. So now, we know the execution engine, we know the runtime, and let's go and try to see how responsiveness has driven innovations in those two, okay? Responsiveness and garbage collection. So responsiveness has given, remember when I said about heap management and garbage collection, I said it was not about reclamation, or not only about reclamation, it was about allocations as well. So to be able to improve responsiveness, allocations have been improved. So for a long time now, the HotSpot virtual machine has faster allocation paths. These are called thread local allocation buffers. These are lock-free allocations where a thread has its own local area where it can allocate out of. So that way it doesn't have to have contention issues and stuff like that with other threads. It only goes and communicates when it needs another buffer area. So it's lock-free. Of course, we have faster reclamation. Some of the GC algorithms have deallocate in place, so it's really fast. Okay, and I'll talk more about that. But just want to list all these things, and of course, more work done concurrently. Remember when I was talking about you don't want your application spending more time in GC. Basically, the application is not doing any work. And that's one of the aspects of OpenJDK HotSpot virtual machine. Most of the GCs have stop the world pause. So that means your application threads come to a full stop, and then GC does its work. And then GC would do its mark, sweep, and compaction in some cases. I'll talk more about that. So what that means is your application is not working. Your GC is doing its work, your application has stopped. So some of the GCs, depending on how sensitive they are to responsiveness, they may do some of the work concurrently with the application. That means your application threads are working, and then your GC threads are working with your application threads. Okay? So that's called doing work concurrently. What about responsiveness and compilation? So of course, I mentioned about ahead-of-time compilation. It helps with improving startup time. So that's one of the things that have just been added in its most basic form in Java 9. We have the adaptive optimizer, and I'll talk about it over this entire talk, because there's lots of adaptive optimizations done in the HotSpot compiler. And then locking improvements, okay? And I'll talk about locking improvements as well, sorry, here shortly. Another place that's important is, that locking is important, is with respect to the runtime. Remember I said interpreter? So when we're talking about locking, the locking instructions are generated in the interpreted code itself. So anytime you have locking improvements, it also helps responsiveness, for the runtime, of course. And then class data sharing. So class data sharing is a particularly important thing because sometimes you have shared code that you want to be able to access. So it's kind of like a shared library or something that you want to be accessed, and then that's called class data sharing. Okay? So let's now talk more about the locking improvements. So over the years, I think maybe since Java 5 or so, up until now, till Java 9, there's been a new improvement added in Java 9. So there, we have seen various flavors of locking improvements, okay? So what are locks? What kind of locks do we usually target? The first kind, of course, is uncontended. So we have a single thread T. It's trying to execute a synchronized method, okay? And that's called an uncontended lock because it's just a single thread that's trying to execute the method, okay? So uncontended locks are also called deflated locks, also known as lightweight locks. So in its simplest form, the lightweight lock would only do a compare and swap instruction. It's called CAS instruction. So this is at your hardware level. So it executes this instruction to store pointer to the lock record in your object header. So every Java object has a header and a body, and I'll talk more about that when I go into details about compressed OOPs and stuff like that. But what we achieve by this is saying that this is locked object, and here is where you'll find more information on it. So it's basically a pointer. Now, what if there was contention? So basically, a different thread U comes in, and it wants to access the synchronized method, which was already locked by T, remember? So now we have contention. And contention is very different. So it's an inflated lock, and I'll talk more about what that means. It's also called heavyweight lock, which means it's not using CAS, right? It's not a lightweight lock. And it does a slower path. Now, what is the slower path? It needs to, so now since you have contention, we need to make sure that we're taking care of the threads that need access to our object. So every object has a monitor, and then each monitor has its wait set. So as threads are contending for my object, they will go and wait in the wait set. Once I'm done with the work, I need to notify, and then these threads can come and access that object. So if I had to draw something, this is how it would be. My object monitor is right there. I have an entry queue. And so you have the monitor enter and monitor exit operation. And if somebody needs to wait, they go and wait in the wait queue. And once they get a notify signal, they come back into the entry queue, and then they can access the object monitor. So that's how an inflated lock works. That's usually done in the slowest path. And up until Java 9. What other improvements are with respect to locks? So remember when I was talking about deflated locks or lightweight locks? I was talking about the CAS. Now, what if I knew that there was only a single thread that was going to ever access it? So I can bias my lock to that thread, and that's called bias locking. You only need to do CAS the first time, and then your thread is known to be biased to the lock. So that's an improvement. So you don't need to do a CAS every time. The second improvement is called lock elision, and I'll talk more about it when I talk about escape analysis. So with escape analysis, we try to find out if an allocation escapes the method or the thread. If it does not, then we don't need the lock anymore, so we can evade the lock. There are other ways to evade the lock also, and I'll talk more when I talk about escape analysis. So let's move on to lock coarsening. So we've seen multiple synchronized accesses to either a method or an instance. What if they were all for the same object, right? So a JVM can identify that. And it says, OK, I don't need to lock every time. I don't need to do a CAS every time. I can just coarsen these and just do it once. So that's called lock coarsening. And then coming back to contended lock. So with Java 9, what happens is instead of doing the slow path, we can based on the path we took already, and we know that it's inflated lock, we can do something called a quick path. It's called quick enter, where you can perform certain things. Like, for example, remember I mentioned about the wait queue? And when the notify is sent, then these guys can go and sit in the entry queue. What if we could just do that as soon as we know it's an inflated lock? We know that it's somebody else is going to get to it, so why not just transfer them as soon as we know it's an inflated lock? So those kind of optimizations have made it into Java 9. So this is how an inflated lock would look. So once you know, runtime knows that it's a contention or an inflated lock, it can do any of those things. It'll go to enter first, and then it'll go the slow path. With Java 9, there is a quick enter, which does these kind of optimizations ahead of time because we know it's an inflated lock. We know that we have reached here for a reason, so we can do certain things that are necessary to be done. So now let's concentrate on footprint. So usually I say, based on the three-legged stool of footprint, responsiveness, and throughput, footprint is the least important. Because most of the optimizations are gone into either improving throughput or responsiveness. But this particular talk, I wanted to talk more about footprint because there's so many optimizations with respect to string that have gone into Java 8 and Java 9 that I wanted to highlight here. So let's first talk about footprint and garbage collection. So compaction and allocation, reducing allocations. So what is compaction? So we have our heap space, and we have reclaimed a bunch of objects. But they may leave, for example, and it does happen in concurrent mark and sweep garbage collector, they may leave holes because you have these live objects and then free space. Live objects, free space, and based on the size of the free space, an object can fit or may not fit. And even though you have space, the new promoted object doesn't know where to go, and that's called fragmentation. So in order to be able to combat fragmentation, what we can do is we can compact. So we can move all these live objects into the lower end of the heap such that we have enough space to promote objects into. So that's called compaction. And most other GCs do that. All of the young generation is compacting. And I'll talk more about the generations and stuff like that, but just something to keep in mind. The other thing is reducing allocations, and that's one of the things is improvements to string, like I said, reducing allocations or deduplication, again, with respect to strings. So we'll talk more about that here. And then compressed headers. So like I said, a Java object will have header and body. Compressed headers are very important with respect to the storage, right? So it's very important with respect to the footprint, and we'll talk more about compressed headers when I talk about compressed oops. Footprint and compilation, we have inlining. Inlining is one of the most important benefits of dynamic compilation. Because you have all these, remember the profile-guided optimizations, you have all this information. So an adaptive optimizer can take that into account, and based on various thresholds, it can do a great job of inlining. The inlining has been studied to the core by HotSpot virtual machine engineers. So, it's one of the best engines that performs really good inlining. And inlining you can do with Intrinsics as well. So we'll talk more about that if we get a chance. But let's talk about escape analysis and deoptimization. So escape analysis, I have an example. Actually, I have a flow chart with respect to escape analysis. What is deoptimization? When I was talking about tiered compilation, we're going through the 5 different levels, okay? And eventually, we're getting to this optimized level. What happens to all this code that's generated? It's stored somewhere in code cache. It's taking up space in code cache. If you're compiled at level 4, which is the highest level, what about all the code that was at level 2 or level 0 or whatever? What happens to that? Well, that needs to be reclaimed. It's called deoptimized. So basically, the code gets deoptimized and then zombied and reclaimed. So that leaves more space in your code cache. So that's one of the optimizations that adaptive optimizers can do. So it's coming to escape analysis. So in the simplest form, you need to just figure out if it's able to escape, if allocations are able to escape the method or the thread, right? So how do we figure that out? It's not stored to a static field or a non-static field of an external object. So if it's an external object and it's a non-static field there, it's still an external object, so it's escaping, right? What about being returned from the method? Of course it's escaping then. What about passed as a parameter to something else? That's escaping then. So these are the things we check for. So remember I mentioned about lock elision? So that's a benefit of escape analysis. First of all, if the allocated object does not escape the compiled method and is not passed as a parameter, then we can remove the allocation itself and then remove the lock as well. So we can keep, instead of performing the allocation, we can keep the field value in registers, right? So that's a beautiful optimization because you're not taking any space on the heap at all, right? There's other thing we can do too. So what if it was passed as a parameter? We still know that we can perform lock elision, so we can get rid of the lock, and then we can use some compare instructions to do more optimized path. So escape analysis, I think, was introduced in Java 7, but it wasn't really functional. And Java 8 onwards, it's really doing a good job. So if you have not tried Java 8 and escape analysis, please do go ahead and try it, because it's not buggy as it was in Java 7. What about footprint and runtime? Okay, so I was talking about compressed oops all the time, and I was talking about compressed headers. So what are compressed oops? We have 64-bit hardware. I was talking about Optron from AMD. That was like the first 64-bit hardware for x86 architecture. What that helps with is having 64-bit operating system, 64-bit applications. The Java virtual machine also has 64-bit pointers when it's working on 64-bit OSs because you can access more heap. But because of that, everything takes space, right? Because now instead of 32-bit pointers, you have 64-bit pointers. So what if you did not need that much heap? What if you needed heap up until, before Java 8, it was less than 32, but after Java 8, it's less than 64. What if you could fit your allocations, everything, into less than 64 gigs of heap? Then you can make use of this optimization called compressed oops and class pointers. Okay, and I'll talk more about that soon. What other optimizations are with respect to footprint and runtime? Code caches. I mentioned briefly about code caches. So when I was talking about deoptimization, so all your compiled code goes and sits in code cache. Okay, and that's one of the optimizations. So basically, you can reuse it. So it's saving footprint because you want to keep this code around, but it's also a cache. It serves as a cache, so you can so it's optimized. And class data sharing. I already mentioned that. So let's look at compressed oops and compressed class pointer. So Java object. Remember, I said header and body, right? So what's in the header? So a Java object header will have mark word, which is native sized, based on your native pointer size, and a class pointer. So and the class pointer is what we compress when we use compressed oop optimization. Now, if this was an array object, then it would also have array length, okay, as a part of your header. With compressed oops and compressed class pointer optimization, what we are achieving is compression, of course, of the object pointer and the class pointer, and it's done by using 3-bit shift. How can we do that? Okay, let's talk about the 3-bit shift first. We can do that because all Java objects are 8-byte aligned. Okay, that's a fact. All objects. So when you're allocating it on the heap, they're aligned 8 bytes. So that means that those 3 bits are 0, 0, 0. So we can use those to get up to 32 bits, 32 gigabytes of addressable space. Right? 2 raised to 35 is equal to 32 gigs. Okay. So this is what it means if you write it down. So you have the wide, which means your full-sized ordinary object pointer, and you can go to narrow, which means compressed, by shifting it left. And then you have a field offset to access the exact field that you want. So, so narrow oops is when you want to store. So you're compressing, so you're utilizing more space. And then wide oop is when you want to read. So when you're reading it a proper 64-bit. And when you're storing it, you're storing only with 3 shift. So you're compressing it, basically. Okay? How does that help us? So if you have less than 4 gigs of heap, your wide oop is narrow oop. Remember? Because it's 2 raised to 32. So you already get that. You already get that. That's for free. It depends on the heap size. What about if your heap size was greater than 4 and less than 28 gigs? That's called zero-based, and then you need to left shift it. You don't do it by yourself. The virtual machine does it for you, and you get that for free also. So when you are 32 gigs, you're not going to get that. So you have to keep that in mind. It has to be less than 28 gigs because of certain calculations and other overheads internally. So when people talk about compressed oops is up to 32 gigs, actually it's only up to 28 gigs. So that's something to keep in mind when you just need the compressed oop optimization, but you're going up to 32. You could try to reduce your heap to 28 gigs, and you will get that for free. Now, what if you just couldn't reduce your heap? It has to be between 28 gigs and 32 gigs. You will still get the optimization, but then you'll have to use the field offset, and basically the JVM is doing it for you again, but it is maybe little less performant than the previous one. So try to stay within 28 gigs if you can, or at least try to figure out if you could reduce your heap until 28 gigs. With Java 8, what we could do is shift the alignment. The Java virtual machine by itself could shift the alignment to 16 bytes. Remember I said it was 8-byte aligned? The objects are 8-byte aligned. If we shift the alignment, so basically now instead of 3 bits, you have 4 bits now that you can play with. So if you could shift the alignment, change the alignment to 16, then you have 4 bits to play with, so your addressable space now is less than 64. So, but remember, because the alignment changed, so we have more wasted space. So you could do your experiments. If you need to go above 32, but you can still be within 64, then try to do an experiment in Java 8 and try to see that. Or you could change your alignment by itself. So there's an option to change object byte alignment, change the alignment and see if enable compressed oops and see if it works for you. So it's the same thing. Instead of 3-bit shift, you have 4-bit shift because of the alignment has been changed. Okay? So the same table, just rearranged. So we have object alignment, we have offset requirement, and shift by. So if your heap is less than 4 gigs, you get it for free. There's no shifting necessary, nothing. Between 4 and 28, you don't need offset. Again, it's called zero-based. So it shifts, the JVM shifts it for you, and you get that. It's not as expensive as the others. Less than 32, you will still get it, but you need offsets. Again, the JVM will do it for you, but it could get expensive. Less than 64 on Java 8, the alignment will change, so it may get very expensive because you're wasting space. And then please go ahead and experiment and figure out if that's affecting you in a bad way. Okay? So with compressed oops in Java 8, you also get something called compressed class pointers. I'm not going to talk about permgen removal, but I have an article out there on InfoQ that you can go and read about it. But with Java 8, we also went and did something called permgen removal. So now your whatever used to be in your permgen now goes and resides in something called metaspace. Okay? One of the benefits of that was that you could also do compressed. You can also compress class pointers. Remember when I spoke about the header, I mentioned about the class, K-L-A-S-S. So, if I took this, I took this from this particular presentation by John Masamitsu and Colleen Fillmore. They presented this at Java 1. John Masamitsu was the project lead for metaspace for permgen removal. So what it shows here is what is important for us to know, because I'm not going to talk about permgen removal, is now permgen is metaspace. And then we have the compressed class space, which is also a part of metaspace. So in compressed class space, you're storing all those compressed classes. Remember I said about the object header, the class? Those are compressed, and you're storing that there. So it saves your metaspace, which is basically your native memory. Metaspace is outside the heap, and it's a part of your native memory. So that's an optimization that you get in Java 8 when compressed oops are enabled. Okay, something to keep in mind if native space is of concern. Okay. So now moving on to throughput and the execution engine and runtime. Okay. Throughput and garbage collection. So to remember the stop the world events that garbage collections do so often. What if it was just single-threaded? That would be really, really bad, especially depending on how much work it has to do, right? So there's an optimization which you get. It's called parallel GC threads. It's by default it's 5/8 of your processing threads available to you, but you can increase it to as many processors as you can give it. So if your application threads are using 16 processors, you can increase parallel GC threads to 16 because that's the stop the world time. That's the time that the GC spends by itself chugging along and doing the GC work. So those are called, so those GC threads are multi-threaded and they do work stealing. So basically if one of the threads, so this is basically a queuing theory, everything done right. I think I may talk more about it if I get some time. But let's move on to something else with respect to throughput and GC. So in order to maximize throughput, one of the things that HotSpot does is, most of the HotSpot GCs, they do that. They have multi-generations, which means there is the young generation where most objects get allocated into, and then they're aged in the young generation, and then they're promoted. So for your long-lived objects, which may and should actually form your live data set, those will get promoted into the old generation, and they'll stay in the old generation. Most of the HotSpot GC algorithms are optimized for the old generation. Most of the young generation algorithms are similar. Actually, all of them are similar. If it's a multi-generation HotSpot garbage collector, all of the young generation algorithm is same. Okay, and I'll talk more about that too. Multi-phase marking, when I get to that, I'll talk more about that too. And compaction. There are two ways now with the G1 GC, with the introduction of G1 GC. Now compaction does not have to be monolithic. So in the past, old generation compaction was monolithic, which means the entire generation was compacted. So usually, if you have used parallel GC in your past life, then you would have seen that there's one stop the world pause that takes 23 seconds or something, some absurd amount like that. So with G1 GC, if your application has been optimized or if it's been following warm-up phase and steady state, G1 GC will do incremental compaction and it's adaptive in a way. So especially more adaptive with Java 9. Again, depending on how much time we have, we'll talk about that, which probably we don't have any time, so probably not. Sorry. But these slide decks are self-explanatory, I hope, and if you get a chance, please get them. Whenever it's available, I'll do that. So I'm going to quickly go through this and talk about intrinsic. Something intrinsic, people do use these kind of optimizations without even knowing. So one of the things is when you have the JIT compilation code, the JVM will put in hand optimized code. So basically somebody went in there and optimized it. For example, array copy. Somebody went in there and optimized system.array copy. And so basically you get benefits of your static compiler. So when array copy and static compiler is optimized, it's the same way, just that it's hand optimized for that particular sequence. And intrinsics can be inlined. We already spoke about the compressed loops and stuff like that. Sorry. So one thing I wanted to talk about with respect to the strings, because I mentioned about strings and footprints and how I don't cover this anywhere else. So strings and footprint, the way we talk about Java objects, right? We have the instance, and then we have the object itself, and there's a backing array, because string needs a backing array, because string is string, right? So up until Java 9, the backing array was a char array. With Java 9, with string density efforts, this is now not char anymore, it's a byte array. So you're saving space right there, okay? I don't have time to go into that, but if you get a chance and if you want to look at string density optimizations, I have various talks on those too, and there may be some articles out there. There's JDK enhancement proposal, JEP. Go ahead and read that, and that's a very useful optimizations, because apparently strings make up like about 29% of your Java heap, like live data set. So you will benefit from this optimization without even you knowing, because there's nothing that you have to do but just move to Java 9 maybe, other than doing all the modular things. I'm not going to go there, but point is that these optimizations have been made. There's the other thing about intern strings also. So what if that was interned? So if you use intern strings, then you get this pool of strings here in your Java heap, and each backing array and the object itself will reside in the pool of strings. And with intern strings, you know that if string 1 was .intern is equal to string 2 .intern, then string 1 equals string 2, right? So what happens? What is the optimization that you get for free? You get, if string 1 and string 2 were the same, what equals, then you just point, the instance just goes directly to the same thing. So you don't have to allocate string 2, knowing that they're equal, okay? So similarly, with respect to G1, GC, and Java 8, this optimization is made in Java 8. You don't even need the strings to be interned. What you need is just to use G1 collector. You use G1 collector, you have those two strings, and if they're equal, it'll just directly point to the same backing array. So you get that for free. So, but you need to be using G1 GC, garbage first, garbage collector, and Java 8. Okay, I think I can still go on because I have a lot of slides, like I mentioned. But if you guys need to leave or you need to catch me later, please go ahead and at Twitter or write to me, at my company's email address. Talking about generational GCs, I wanted to talk about the generational principle, which is young generation and old generation. I was talking about that. Young generation is Eden and survivor spaces. And the way it works is very simple. All of the young generation is divided into Eden and survivors. So you have survivor 0 and survivor 1. Most allocations happen in Eden. And then all the live objects after a collection are moved into one of the survivor spaces. And that's kind of like a sieve where you age these objects. Okay, based on this age threshold, which is inbuilt, into the algorithm, and you can change it on the command line, of course, you will get these objects that can get promoted. I think the default is like 15. At age 15, they get promoted, but it may change with different GC algorithms may have changed their algorithms. So after the aging threshold is crossed, you tenure it. It's also called promoted. So if I had to talk about the optimizations and classify them based on allocations or reclamations, that's how I would do it, but I already spoke about those, most of them. So let's look at some allocations optimizations. So I mentioned about thread local allocation buffers. It's based, most of the allocation, because most of the allocation happens in Eden, so most of the allocation optimizations happen in Eden, right? So your Eden space is divided into these allocation buffers. And based on the number of threads, you have those allocation buffers. They will be sized based on the allocation patterns of your thread. And the number per thread also depends on how fast a thread is consuming them, okay? So in this case, I have 5 TLabs because I have 5 threads. Once Eden gets full, survivors happen. There's an optimization that is working with parallel GC for a while now. And this was based on the experiment that I did when I was working with Optron. So Optron was not only 64-bit, but also it did NUMA, was an NUMA architecture, which is non-uniform memory access. And that's how it looks. So you have different processing nodes, and they each have their memory controllers, and each controller is controlling a memory bank, DRAM bank. So if there is something happening, if a process is running on node 0, but it needs to access a memory bank on node 3, it has to go 1 hop and 2 hop. So like that, you know, or it could go from node 0 to node 1 to node 3. So there's 2 hops away, and then if it was on the same one, that's 0 hop, and then node 2 would be 1 hop away. So that means that you're accessing memory in a non-uniform way. Previously, all of the processing nodes would go to a single memory controller and to the DRAM bank, so everybody has uniform access to memory. But with this architecture, it changed the way memory could be accessed. So again, with NUMA allocator, now the JVM can have Eden space in sort of regions such that you have area for node 0, you have area for node 1. So if a thread was running on node 0, it'll do its most of the allocations locally, right? So the thing is that, or the hope is that the thread is not moved. There's not too much of context switching. So that way you get the NUMA benefit, so you're going only local hop. There's no hop, basically. You don't have to go to a remote thing. But what happens with old generations or with survivors? They are interleaved. So you go chunk-wise. So little chunk here, little chunk here, little chunk here, little chunk here. So the Eden is local first. It's based on the first touch principle. Whichever thread touches whatever local area, Eden space will be allocated out of that area. And then others are interleaved. So that's how NUMA allocator works. It's only available on parallel GC. G1 GC will get it too when there's time to do it. So there is an RFE for G1 GC to get NUMA allocator as well, but it hasn't been implemented yet fully. These are the optimizations. You can go ahead and research that. I was going to talk about reclamation. So like I said, similar GC algorithms for generational OpenGDK hotspot, but the only difference is in the old generation algorithms, okay? So we have 3 different kinds that I want to cover here. The first one is called parallel GC. It's also what I like to call throughput maximizer. So it has multi-generational heap, of course, young and old generation. It has multi-threaded workers. Remember the parallel GC worker threads count that I mentioned. Compacting collector, it's a monolithic old generation compacting, which means the entire old generation will be compacted. Faster reclamations via PLabs, which is promotion local. So similar to TLabs, we have when we are promoting, the garbage collection can make use of. So T labs are by threads, by allocating threads, right? Your application threads, basically. P labs are by GC threads. So your promotion labs are basically your GC threads are promoting. So these are P labs. They're only available in the old generation, or maybe in the survivors too. I don't know for sure. Sometimes it may be depending on the GC algorithm. The other one is CMS. It's deprecated in Java 9, I think. The difference is, again, in the old generation algorithm. So you still have multi-generational, and you have multi-threaded workers, especially for the young generation. You have some multi-threaded workers for the old generation where some of them are stop the world, okay? And it's multi-phase marking. So it does, so like CMS is concurrent mark sweep. There's no compact. So there's no compaction. And that's why CMS is prone to fragmentation. CMS has other issues, which it goes to concurrent mode failures and other issues. So that's why one of the things is like the GC engineers don't want to support it anymore. So what's happening now, Google and Twitter and others are like doing these, they're doing compactions, adding compacting algorithms to CMS. So because most of their workload depends on the way CMS works. Because one of the things is that it does in-space deallocation. So it does sweep really fast, right? So that's the CMS algorithm. That's why it's latency sensitive, because there's no compaction. You're not compacting. There's no stop the world pause with respect to that compaction. So you're doing quick, just deallocating in space. So sweep is pretty much free with CMS. G1 GC comes along, and one of the optimizations, one of the major thing about G1 GC is regionalized heap. So now your unit of work with respect to garbage collection is reduced. Previously, remember when I said old generation is monolithically collected? So your unit of work is like the entire old generation. You couldn't divide into chunks. I mean, you could internally, because you do the pages and all the pointers, the card tables and stuff like that. But when you're collecting, you're going to take a monolithic old generation and you're going to collect all of it. With respect to G1 GC, the unit of work is a region. So basically, you can add your young generation plus one of the old generation region, and that's all you have to collect. So that's why you can do it incrementally. So those are called mixed collections. So basically, mixed collections will have one or more regions out of the old generation. And basically, that's the way G1 GC works. It's more, the algorithm adjusts itself based on your pastime goals, your live data set, and the size, of course, of your heap. So these three things help the algorithm tune itself in a way. And with Java 9, it has adaptive thresholds, which means that your marking can start in an adaptive fashion, like it used to be in CMS. So if I had to do some draw where I could do, say, throughput maximizer versus latency sensitive GCs, G1 GC would be in the middle because it takes care of your throughput as well. I think that's pretty much it. I was going to talk about what compilation thresholds are, which you can just look and read from here. And tiered compilation, different levels of tiered compilation. And yeah, so the adaptive optimization, which is with respect to the hotspot virtual machine, is something very important because we do profiling of hotspots, but we also do adaptive JIT optimization. So if I had to draw it, it means that I could go, based on my tiered compilation levels, I could be doing this for a while. Right? I could be JIT optimizing myself, and that's the beauty of hotspot virtual machine. Eventually, I could just give up and go back to interpreter because I don't think it needs to be optimized, or the method is not hot anymore, right? So you want to go back to the interpreter. So that's adaptive optimization that comes for free with hotspot JVM. And dynamic deoptimization, why do we need it? We have dependency invalidation, classes getting unloaded, uncommon path, misguided profile information, of course. I think I should just walk out because I know this next speaker may be here somewhere. I'm so sorry I took a lot of your time. And thank you, guys. Thank you for staying.